Doors opening. Please select your floor. Doors closing. Third floor. Doors opening. Please select your floor. Doors closing. Ground floor. Doors opening. Third floor. Doors opening.
Let's take a look at the forces acting on that man as he stands on the lift. And we presume that he's standing on a weighing scale as well. The weighing scale is part of the floor. Think of it that way. Let's take a look at the man. There he is standing there. And there's two forces acting on that man. The obvious one is the man's weight, which is acting downwards. And there's another force acting on the man, and that's going to be the normal force, which is acting on the man. Now, where does the normal force come from? It comes from the floor pushing up on the man. The normal force is the floor pushing up on the man. And that gives you a clue, because as the floor pushes up on the man, presumably it's pushing up on a weighing scale. It's squashing the springs. So the normal force is going to give you an indication on the scale of the person's weight. Now, when the lift is stationary or moving with a constant speed, then what we can say is that the normal force is going to be exactly equal to the weight. There's going to be no unbalanced force there. The normal force equals the weight of the person, N equals mg. So you're just standing there, you're going to have the forces balanced like that. As long as the lift is not accelerating, it's moving at a constant speed. But what happens if the lift is accelerating? Well, in this particular case, we have to bring in an unbalanced force. And there's an unbalanced force there acting on the man. Now, we can make an equation from that. We can say the unbalanced force is equal to all the forces acting upwards, which we know is going to equal to the normal force. Subtract all the forces acting downwards, which is going to be the weight of the person. And we also know that the unbalanced force is always equal to the mass of the object, and it's going to equal to the mass of the object times its acceleration, which is going to equal to the normal force, take away mg. Now, I'm interested in that normal force N, because that gives me the expression or the equation of how the force pushing up on the man by the floor is going to change when things accelerate. So we can rearrange that to get N is going to equal to the weight of the person, mg, plus ma. Now, this is the key equation. It will not be in the relationship sheet. You should be able to derive this, but it's a very powerful equation. And what it's telling us is that the normal force, the force of the floor pushing up on the man, is equal to the weight of the man plus any acceleration, any unbalanced force, which can be calculated by ma. Now, things do get tricky, because the lift accelerates upwards, it accelerates downwards, it decelerates upwards coming to a stop, and it decelerates downwards coming to a stop as well at a bottom floor. Now, to understand this, we have to look very closely at the velocity time graphs, because we can look at the velocity time graphs as what's happening. We can decipher the acceleration, because the acceleration after all is just the gradient of these graphs, and then we can work out what the normal force will be, because whatever value the acceleration takes will be the value ma takes. Let's take a look at the first scenario. We'll slide down, look at the first graph. And there's the first graph there. You can see that the velocity is increasing in the upwards direction, because up here in this part of the axis, above the t-axis, we take everything that is going upwards. If it's down below here, we take it that everything's going downwards. That's just our convention. So in this case, we have got a positive gradient. The lift is accelerating upwards. So the lift is going to accelerate upwards. Then what's going to happen to N? N is going to equal to mg plus ma. But the acceleration is positive, which means ma is a positive number. So you're going to get N equals the weight plus another number. Therefore, we can say that the normal force is going to be greater than the weight. So the reading on the scale when you accelerate upwards becomes bigger. Let's take a look at another example then. here's the case, the second graph here, where you're accelerating downwards. Notice the graph is we're going below the graph, so anything below here is downwards, and this line here tells you the velocity is increasing downwards. We're accelerating downwards, just as it's leaving maybe say the third floor. So what's the gradient here? The gradient is going to be in fact negative. So the normal force, if we're going to be accelerating downwards, then we're going to have this situation. So that's going to be accelerating downwards. N is going to equal to mg plus ma, but look at the gradient. The gradient is going to be negative, which means ma is going to be negative, which means that the normal force is going to have the weight take away a number, so therefore the normal force will be less than the weight. So the scales, when you're accelerating downwards, when you're going from the fourth floor to the third floor, momentarily when you're accelerating, your normal force, which will be the reading on the scale, will get less, as we saw in the film. Now come the two complicated ones which we can solve with our velocity time graph. Let's take a look at this one here. What's happening here? The velocity is decreasing and it's going upwards because we're in the up part of the graph. So the velocity is decreasing upwards. So therefore what we're doing here is we're decelerating upwards. Decelerating upwards. The lift's coming to a stop in the upward direction. We're decelerating upwards. You can see the velocity is becoming less and less and less and less. So we have n equal to mg plus ma, and remember the acceleration is the gradient, and you can see that the gradient is going to be negative this time. So we're going to have a ma to be negative, and therefore in this case n is going to be, if it's going to be a negative number, n is going to be less than mg, because the gradient is negative and therefore the acceleration is negative, and therefore we've got a weight take away a number, and we're going to get mg, which is going to be, we're going to get the normal force less than mg. So when the lift is decelerating upwards, coming to stop upwards, you feel lighter. You see the scale becoming lighter. And the last one is perhaps the most complicated one at all, but we can use our velocity time graph to explain it. And it's this one here. When we have this situation, the velocity is decreasing, and it's going to be a downward direction. So the velocity is decreasing in a downward direction. And what's going to happen here? We're actually decelerating when we're going down, decelerating downwards. So that's the situation where the lift is coming to a stop at the bottom floor. Look at the gradient. The gradient is going to be positive, because if you look carefully, the velocity is becoming smaller and it's in the downward direction. Remember, below the axis here, below the zero axis here, everything's going to be going downwards. So therefore our equation n equals mg plus ma, and let's think about this one. We're decelerating downwards, we have got a positive gradient. So n is going to be greater than mg in this case, because ma will be positive. So when you're decelerating downwards, when your lift is coming to a stop, when it's going down the way to maybe the bottom floor, you feel heavier, because according to the equation, the normal force will be greater than the weight of the person. So I hope that's helped to explain the lift equations. It's very, very complicated, but if you look at it in terms of the velocity time graph, you should be able to work you through the situations. Hope it helps.